Another bag! Welcome to the final physics lab brought to you by Jake Bernstein. This one is magnetic molasses. A brief overview, I'll provide an introduction, then experimental results, a computational model, discussion, and finally a conclusion. So the purpose of this lab is to observe and model the motion of a falling bar magnet through a cylinder of conducting aluminum foil, and then compare the computational and experimental models. I'll let you read the assumptions and results. Now, concepts and formula. The overarching concept here is relating EMF to magnetic flux via Faraday's law. We also have Biot-Savart law, which is the dominating magnetic field equation. Then Ohm's law sneaks back into play here, as well as Newton's second law. And then the last two equations are a little bit more niche, but the magnetic flux of a dipole and magnetic force on a loop will also come up. So here's the actual experiment, where we have a bar magnet falling through the aluminum tube. I'll let you read the procedure right there. And now, the lab asks what would differ if the aluminum foil were actually steel tube, and we wouldn't be able to use steel because the iron in the steel will interfere with the magnetic field of the bar magnet. So that wouldn't work. And then as the magnet falls down, essentially a few forces are at play. It's being pulled down by gravity, obviously, and then it also induces current in the top and bottom, which oppose the force of gravity. Now here's a video of the experiment.
Where'd it go? Oh my god.
I'll save you from the profanity at the end there. Very cool experiment. Now here's the code we use to model this experiment. I'll let you sift through it by yourself, but essentially on the left we're establishing our physical constants. On the right there we have our tube. We implement a for loop to make the tube. And then it got cut off a little bit, but we're defining our B field for the dipole as well as the flux of the dipole. And then that behemoth on the right is essentially iterating through each loop in the tube and calculating both the force and flux acting on the bar magnet. So our theoretical model versus our observed. Our predicted time was 1.465 seconds and actual was 1.42. Pretty small margin of error. And some questions that arise with the theoretical model are relating to the intensity of the color of the tube. I believe red is an induced current clockwise because as the North Pole is falling, the arrow of negative deflux dt is pointing upwards, meaning induced current will be clockwise in red, and the opposite is true on the bottom in blue. It'll also be pointing up, but it's counterclockwise. The dynamics of the system, when you flip the magnet, the currents will still be pointing up, but the current will be going the other way. How does total time in tube compare to computational system? We already talked about that. And we can make the computational system more accurate by adding more rings, if that makes sense. What does the shape of velocity versus time plot tell you about the forces at play? That just says that the forces are non-constant. Here's our discussion. Some sources of error include interference from surrounding magnetic waves and obviously human error. What if the resistivity of the conductor were reduced as close as possible to zero? We saw this in Ohm's law where I equals E over R. Now if R essentially goes to zero, the the induced current skyrockets, and I guess the bar magnet will be in the tube for far longer. If holes or slots were cut into the tube, however, that would interfere with the magnetic field and the bar magnet would fall quicker. Now here's our conclusion. We successfully confirmed Faraday's law the 2 times closely aligned, and we demonstrated how moving magnetic fields interact with conducive material to generate opposing forces. So all in all, this was a success. Have a great day. Thank you.